Second part for chapter 20 on carbohydrate. We're a little bit complex. I would like to invite you to watch some videos, look at chiral and achiral object, shoes, table. You have example in your textbook. So a chiral compound lacks a plane of symmetry, and you'll have what we call enantiomer. They come in pairs. Either they are on a right-handed form or a left-handed form, so D or L. Here that picture shows you the D-glyceraldehyde, that's right-handed, and then the image L-glyceraldehyde, which is left-handed. So there is no plane of symmetry. We're going to look at the effect for this. Let you read that section that shows you what it's important. Well, it has to actually deviate, rotate the light of a polarized light that is passed through a pair of enantiomer, and that's where we actually have some definition textual level. So that's what you have right there, and just example there, and this is confusing. You have a few exercises. Pay attention to the fact that the first thing you have to do will be to determine how many chiral carbon you have in a molecule, and then from here you can actually find how many enantiomers you have. We'll have example right after. So what we're looking at here, you have for the aldotetrose, so 4 carbon atom, 2 chiral carbon that can exist then in 4 isomeric form, because it'd be 2 to the power n, n being the number of chiral atoms that you do have. And when you look at the figure at the bottom, you see that here erythrose and threerose as stereoisomer, they are not mirror image of each other. So we call those diastereoisomers. Convention, we determine that the carbonyl group and the terminal CH2OH are drawn pointing to the right. And the reason is going to be because the bond between the carbon atom and the other carbon that exist are able to freely rotate, and so they will not change the symmetry of the molecule. So don't get confused. At first it's confusing when you see, oh, it's a mirror image, but how come my CH2OH is not on the other side? Well, by convention we put them on the right side. And then other example right here where I talk about D and L, where this is where we have monosaccharide. They are divided into a D sugar or L sugar, and this comes, it's kind of a little bit easy. L is going to be the one that goes for levo, left, and D goes from dextro or right. It's Latin, but the easiest way for you to memorize just L is left, and then you will know that D is right. So those are here example again. So remember the convention, the CO and then the CH2OH are on the right side, but you see that those are on a mirror image, the same molecule, but just you can fold it. So you have the D-glyceraldehyde on the left side, and then the right side is the L-glyceraldehyde. So that handness is very important. I'm not going to go over the Fisher projections because I think it's a little bit more complex. But just look at this, the 2 pairs of aldohexose enantiomers. So you look at here that carbon atom is chiral, so that's why you can have the D-allose or L-allose, and they form 4 enantiomers. So this is where you have the chiral carbon atom farther from the C double bond oxygen, and you have here D-allose or L-allose, D-glucose or L-glucose, and you see that they are mirror image of each other. This is a work example. I would like you to work on that. Identify the following monosaccharide as either D or L ribose for A, or D or L mannose. So how do you do this? Well, you need to check the location of the OH group on the chiral carbon atom farthest from the carbonyl group. So this is here, the one that is right above the bottom one. The OH group point left is a L enantiomer, and when it points to the right side, it's a D enantiomer. So the solution here in A, you see that the OH group is pointing to the right, so it's a D ribose, and the second one is a L mannose because OH is pointing to the left.